And I would like to introduce our first speaker from our dear partner Rivian, who have a great car in the expo zone, which I invite you all to go and try. Veljko Tanjga. He's a tech lead at Rivian. He's here to talk to us about scaling distributed systems while keeping costs low. Whether you are an engineer or a data enthusiast, you will have a greater understanding of how to build robust and cost-effective platforms. This is something I don't understand much about, but Veljko does. Veljko, welcome to the stage. You have a ticket?
Oh, no. There you go. Thank you. So, good afternoon. Hope you had a great lunch. I'm Veljko from Rivian, and yeah, I would like to give you a talk about our data platform. Basically, more specifically on infrastructure that we are running, how we do it, how are we doing it, and how are we keeping it scaling and still optimized for the cost perspective. Yeah. So I would also like to first introduce you with our product. One of these cars on the left side, you can see it in the expo zone. And those on the left, those are the ones that we are actually producing right now. They're in production, they're on the streets. And also we have 3 on the right side, and we are actually actively working on them, and hopefully in 2026 we will see them in the streets as well. So yeah, this would be something like what we call the bird's eye view of our data flow architecture. We have a car, because this is the infrastructure that is serving data that is coming from our vehicles. And in the specific case, we can see from the left side cars emitting some data, and we basically roughly can split them up into 2 major categories, and that's high fidelity and low fidelity data. And low fidelity data, they are coming as they are produced, and they are coming to the cloud immediately. And we can query them, we can access them, we can make decisions based on those data. And also we have something called high fidelity data. And when they are huge compared to those low fidelity data. And for that to actually be ingested into our cloud, cars are usually connected to Wi-Fi or something like that. So yeah, cars emitting data, we have this black box that is doing the magic, and on the right side we can see all the groups of people who are benefiting from all the data we are ingesting and processing and serving to our users, whether they are end users, they have their phone, they can see in the real time data related to their own vehicles, but also like engineers, servicemen, and analytics, and all of them. So to actually make this happen, we will be focusing today mostly on real-time processing. And when it comes to real-time, there are 3 kind of key components that we are using. So this is Flink. It is our stream processing framework that we are using. Also Druid. This is our OLAP database of choice. And Kafka as a distributed event streaming platform. So this is kind of simplified version of it. So we can see that there's a car emitting 1 piece of information, of data, that are sent to one of our services, and then forwarded to one of the Kafka topics. From there on, we have a Flink job that would start processing this data on the event base. So its job would be anonymization, standardization, checking the validity of this data that is being ingested, and after that it's placed in another Kafka topic. From there on, also different jobs are there to pick up the pieces they find mostly interesting to them, and there, of course, are after that placed to other Kafka topics. From there on, different services are processing, and for us, the most important user of this data in this Kafka topics is our Druid database. So Druid database would serve as a at event ingesting database, And after that, after Druid ingested all those data, those data are available to our users through one of the services. We can also differentiate two types of using this data. So we have Druid, and we have the users that we already mentioned, like how are they using those data. We also have something we are calling event watch service. And this is actually something that we are created to trigger an event on an event per event base. So if some certain condition is met, we can actually trigger some service or send it somewhere or process it, notify someone. So for all this to actually work, what do we need? We need scalability of our platform, we need reliability, and at the same time, it also has to be cost effective. So what are we using for this? Obviously AWS. They have excellent services, and we are using it whenever possible. And also, one of the key components of our infrastructure is Kubernetes, of course. And some services that we are running are AWS provided, like the aforementioned Kafka as an MSK service. And we also use EKS as a hosted service. But Druid and Flink, we use them as open source solutions, as is. And Flink and Druid, we are using operators to manage them inside our Kubernetes clusters. And why? Of course, we have all sorts of advantages of using something so developed and mature as Kubernetes. So mainly self-healing and rolling updates. We also benefit from abstracting the underlying infrastructure. We can also always move to some other solution if we find it more convenient for us. But also we have Manifest as an easily understandable API. Instead of managing different components, we can just write simple manifest, Kubernetes manifest, and have everything just work. And yeah, we benefit from vast Kubernetes ecosystem. Like we can use Helm charts, we can use Customize, we can use Argo CD, all sorts of stuff. So everything we can use, we can also use that to manage services like Druid and Flink. So let's talk about Druid a little bit. Druid is quite a complex animal, and it's built in a way. Its architecture is such that there are multiple components that can be configured and scaled independently. So we have controlling segments like master services, we have query services, and also data services. So all of them can scale independently as needed. So what I want to focus from this diagram specifically are two components, mainly middle managers and the historicals. So what are middle managers? Middle managers are serving ingestion purposes. So they are subscribing to one of the Kafka topics, and they're ingesting. But at the same time, when they actually get this piece of data, that data can be queried. So it doesn't have to be packaged and placed to another index file like those that are already living on historical nodes. So this is really great. And the way it works, it actually is those middle managers are deployed as either stateful sets or deployments, and they're serving like as placeholders. They're always running, they're long living. And they ingest data, they're creating index file of all those data for one period of time. It's configurable, but let's say 1 hour. And after that, they are handing it over to S3 bucket. This is deep storage that we are using, and it serves as a backup, let's say. So if you lose the whole Druid cluster, we can restore everything and still have our data, safe. So what else? We have historicals. Historicals are actually what is keeping this data and providing them to our end users. And historicals are the ones that are getting those data from deep storage and serving it. And they are queryable through brokers, one of the other components. Okay. So like I said, let's focus on two key components, historicals. They're served as a data storage, and middle managers as ingestion processing units. And with all that being said, how can we actually improve this? Because we have a system, we have a platform, it's working great, it's serving us really well. So yeah, cost control. Common theme, however it's good, however we are configured it, and it's already, not cheap, but inexpensive. We can always do better, and we are actually constantly looking for ways to improve it and to, pay as little as possible. Yeah. And why is this the case? Because when we are dealing with large amounts of data, we are paying for moving it around, so moving all those data from one Kafka partition to another, to the Druid, to the it's moving data all the time, and those are huge amounts of data, and it's costly. Also, we are paying for processing all of those data, so either whether it's Flink processing data or middle managers actually ingesting it, and we also pay for storing data. So we have all kind of different storage solutions, like local EBSs, like network drives, and object storage like S3. So we need to find a way to better use all of them. So we can still keep costs down. So let's talk about how can we actually improve our processing in a way that we can cut costs down. So we actually switched to, for almost all of our workloads, to Graviton instances, and just by changing our architecture to ARM, we cut 20% of our bill related to processing. We are also actually did some rewriting application. So just by rewriting one of our extremely demanding application from Python to Rust, we cut the number of pods running it to 10%, just by using another language. And another thing that we also did is we moved from cluster autoscaling to Carpenter. And in case if you don't know what the Carpenter is, it's actually in charge of requesting nodes, so EC2 instances in your Kubernetes cluster. And Carpenter is really, really aggressive. In a way, it really tries to squeeze and use all the space you have in a way that nothing is left. So every EC2 instances you have is 100% utilized. And if it's not, there's going to be some rebalancing so that all of your nodes are used optimally. And to actually achieve this, you need to really have your requests and limits in Kubernetes for each application running there configured properly. Because if you don't do that, you're going to be in trouble. Because Carpenter won't allow those kind of things. You're going to have some processes that are using more CPU than is actually available in the cluster, and it doesn't end well. How can we save on our storage bill? First of all, we started investigating different storage solution for our Kafka, so MSK service. So the way Kafka works is, it has some retention period, and to actually be on the safe side and not lose any data, we have that configured rather, on a safe side. So bigger time frame for all the data to still live in our clusters. And but yeah, that's also expensive. And most of the time, we don't need all those data kept for so long. So this is why we were investigating MSK tier storage, meaning we can still save our data and keep them in case we actually need them at some point in time later on. But we actually moved older data to object storage, and that's basically S3 bucket. The second one is not really a brainer, so EC2 instance type. If we can have, and we can have, tiered data sets in Druid, we can actually use more expensive, more performant nodes for the types of data that is more accessed more frequently. And for those, because Druid is a time series database, so older data we can put them on a lower cost instances, and we're still going to be fine. And also one of the recent additions to Druid is introduction of querying from deep storage, so from S3. So that's also something that we can investigate. Networking savings. So that's also a big one, a big part on our bill. So, AWS will charge you for inter-AZ communication. And basically every service that you are using in AWS, if you want to be also on the safe side, in case of any disaster happen in one of the availability zones, you're gonna wanna have your workloads spread on on at least 3 availability zones. But you also at the same time would want to keep the intercommunication between the availability zones to the minimum. So we actually configured, for example, our Flink jobs to communicate and to process data from a partition, Kafka partition that is placed on the broker that's in the same availability zone. So this really helped to cut the cost on the networking side. Aside from that, we can also look into like topology-aware routing that would also provide you with the configuration that you only allow or prefer communication to the services that are in the same availability zone. And also one of the other things that you can look into is internal traffic policy. That's also settings you can enable on the service Kubernetes object. Yeah, so what would be the next? As you may or may not heard, Rivian and Volkswagen created joint venture. So what would that mean to us? The platform that we are using right now is scalable, it's highly available, it's great. But, and all the different components that we are using can scale really good, but not indefinitely. So at some point of time, one of the services can't be scaled anymore, at least not neither vertically nor horizontally. So what we actually do, in that case, if only one service needs to be scaled more than possible, we can use something called sharding. So we can shard our data for the same customer, same data set into 2 services different. Let's say we can have 2 Druid clusters for the same customer. But if we are going to having much more cars that we have now, and obviously because of the scale of the thing, and Volkswagen is much bigger company, and they have 72 factories. We have 1, and we will be having 2 in a year or 2. So to actually provide solutions for that kind of workload, we can look into something else, and that's called cell-based architecture, which basically means we could have all the components that are making our platform like duplicated, provisioned, and made available to only certain subset of vehicles. So usual use case would be we would be having one cell for Rivian. We could also have another one for Volkswagen. We can also have different cells for vehicles in different regions. So if you are buying your car in Europe, you wouldn't want to send those data to US and vice versa. So how can we actually do this? So we started working on a solution to provide this platform very fast, very reliable, and this is why we started working on a solution to provision it automatically using Crossplane and Argo CD. So these are kind of really great match, and we do get all sorts of benefits by using those. So Argo CD, it's a continuous delivery tool, implementing GitOps. And Crossplane, this is a cloud-native control plane framework. And you can think of Crossplane as a tool that provisions infrastructure, but unlike Terraform, which is CLI, doing the job. So if you want to automate that, you would use that in some CI, like in Jenkins, in GitHub Actions, that kind of things. But Crossplane is actually a controller running in your Kubernetes. So you can describe your infrastructure as, again, Kubernetes manifests. So, and you can also, like in Terraform, group different pieces of infrastructure together to create something called Crossplane composition. And that way, you can build huge parts of your infrastructure just by applying one Kubernetes manifest. And cross-plane controller will take over and apply that for you. And one of the biggest advantages of that compared to, say, Terraform is that it doesn't have to wait for dependent resources to be up and ready, because Terraform works as a CLI. You execute it. If it runs into an issue, it would break out. It would fail. With crossplane, you would have a situation where it's like it would, as any controller, running in a loop. So it would try to create some resource. And if it figures out it doesn't have all the necessary dependent resources, it would just wait, try again, and try again. And after some time necessary for that to be provisioned in AWS or Kubernetes cluster, whatever we are using, because we can provision all of those with this tool, you would have your platform up and running and ready to ingest data. That's pretty much all I've had for today. If you have any question, I'm all here.
Over there. Question over there. And over here. Sorry, thank
you. Sorry. Hello, thank you for your presentation and getting so deep in the technology stack. I was just wondering about your opinion after doing this, changing from Python to Rust. You showed that, okay, you could save probably a lot of money on machines, but I imagine that whole team had to learn a new programming language, maintaining this, monitoring, probably some, libraries were different. Do you think it was a good move, or could you just share your thoughts about this?
Yeah, that is usual obstacles to adopting another way of doing things. But we are, as an engineer, we are constantly learning. The things that you were working with 10 years ago are not the same things that you are working with now. So if you want to improve yourself, improve the things that you are working with, and have some good benefits for your company, you will learn another language, because if you have knowledge on one, you can pick it up on the other one. It does take time. There's a learning curve, obviously. But there's also this moment where programming languages like Rust and Go are really popular, and people are going to start learning them anyway. And considering the benefits they are providing us, they are picking it up.
Yeah, thanks.
All right, we have another question here. Two questions indeed.
Can I have also a question?
A follow-up first.
So I see in your infrastructure you have you do a lot of self-management. You are on a cloud, but it is like cloud is a VM provider, not much more. So any second thoughts or pain points with that? For example, coping with updates. An open source has this setup where you have a lot of updates that might be not compatible and so on. So you need to manage this somehow. So any thoughts, any opinions on how much does it take of your capacity?
Yeah, there's always like a trade-off when it comes to whether you're going to use something you are going to self-manage or have someone else to manage it for you. Well, to start with, we are using AWS. We are not managing our data center. That would be too big of a challenge, or it would require much more manpower and whatnot. So we are using what we, are thinking at that time is the best for us to use. We do, for example, you are using Kafka, so MSK, that's actually AWS provided service. But we are evaluating, is it the best tool for us to use now? Maybe it's not going to be the case in a year or something, and at that point of time, we might start to manage it ourselves. And there's always like the overhead in terms of management and tracking it all down. It certainly is much more easier for someone else to do it for you, but there is also some advantages of having the full control over your system. a good example is also like Kubernetes. We are using actually EKS, so that's AWS provided Kubernetes cluster. We are managing our nodes through Carpenter, but master plane, we don't manage that one. So it's a trade-off. We do it on a case-by-case basis. So if we think this is going to be too costly for us to have provisioned AWS provisioned or by other party provisioned service, yeah, we're going to roll our own. And if it's not too big of a impact to our costs, so yeah, sure, we would use what other can provide to us.
All right, thank you. We have a question here, and to conclude, a question here. Too many questions.
Hey, first of all, thank you for the talk. My question is, do you have one centralized place, for example, Kafka cluster or something like that, where you store all of your data across the world from all your cars, or you have like different architecture with something like distributed and multiple AWS regions? You send data and collect data.
It's also depending on the workload, because this is only the part of our, let's say, cloud stack that we are using. One of those, the one I presented today, is used as a cloud vehicle service. So here we are using one Kafka cluster that is also, of course, highly available and durable. But like I said, at some point in time, that can be, it could be problematic for us to scale anymore horizontally. So in that case, we would actually use the sharding paradigm that I was talking about.
Okay, thank you.
All right, thank you. We have one last question here, and we'll see, because we are running out of time. But Veljko will always be present at the conference and also at the booth. So if you have further questions,
you can ask him. Yeah.
Okay, go ahead with the question.
Okay, thank you. Yeah, hi. Thanks for the talk. It's interesting to see all the services working together. I was just wondering quickly about the crossplane. Can you elaborate a little bit more on the benefits of using crossplane versus, let's say, Terraform or CloudFormation? And you mentioned the retrying that comes out of the box, but I'm pretty sure it could be done with Terraform as well. And why is that necessarily a benefit in your use case? Or if there are any example of other use cases where you would choose such a behavior as a default? Yeah,
what crossplaning is doing is constantly reconciling what is defined in your manifest with what is the actual state of the world, right? So if you configured some AWS resources as a Kubernetes manifest, crossplane will constantly sync those changes, check on those changes, and let's say someone with fat fingers deleted some of your resources, crossplane will bring it up. So that's one of the advantages that we have with tools like crossplane, but we do not have that with Terraform. Terraform is like, you have to click it, you have to do it manually to actually expect it to bring back your infrastructure back into place. We actually had recently some situation, so to say, in one of our development environments where 20 name spaces were deleted. And we had some of those services managed by Argo CD, which is also doing the same thing for manifest. But what is reconciling is state in Git and Kubernetes. So what happened is all of those came back. So we had namespaces deleted, they came back, and they're up.
Thank you.
All right, and the last question here.
Thank you for the talk. Now, the question is regarding the stream processing. Can you please just, in short terms, tell what was, in your use case, the reason for choosing Apache Flink over other stream processors?
Actually, you could also use like something like Spark. But let's say Flink is built as a processing engine, first and foremost, with the batch processing as a second thought. And when it comes to Spark, it's the other way around. They both can do both things, but Spark is built as a batch processing, and this is an add-on feature to use it as a stream engine.
Okay, thank you.
Thank you very much. Thank you very much for all your questions, and thank you very much, Veljko, for sharing your insights and expertise with generosity. Please, a big applause for Veljko.
Thank you.